this afternoon is by Tom Sanders from Oxford. He will speak about Roth's theorem and application of approximation groups. Approximate groups.
Right, thank you very much. Hopefully, we can get to a good height. Okay, yeah, so first, can I say thank you for the invitation, the opportunity to speak. It's a great honour to be here. I'm going to talk about Roth's theorem, an application of approximate groups. And the talk will split into about 3 sections. Okay? So the first section will cover Roth's theorem and what it is. The second is going to be a little bit on why you might be interested in this question. And in the third, I'm going to try and do a small amount of proof to explain the connection of approximate groups with Roth's theorem. I hope to convince you that they're natural and useful in this context. So that may be an optimistic move. The motivation for Roth's theorem, if you like, comes from number theory and to some extent combinatorics, but the techniques I'm going to talk about are analytical. Okay, so so the starting point for this problem is this question. Do the primes contain infinitely many arithmetic progressions? Okay, and what I have in mind there are sort of proper arithmetic progressions like 11, 17, and 23. So that's going up by 6 each time, and not 19, 19, 19, something like that. If I do need to, and at some points I will need to distinguish between these, I'll talk about perhaps non-trivial and trivial, respectively, and perhaps proper and I guess improper. Okay, so formally then, we're looking for distinct primes P1, P2, and P3, such that P1 plus P3 is equal to 2P2. And I'd like, if you can, just to sort of keep that equation in mind, that sort of x plus y equals 2z as an equation in mind. Okay, so that's a question you could start with. It will turn out for us that it's better to ask a slightly harder question, I suppose. How many arithmetic progressions of primes are there? So you can envisage at least 2 different approaches to the first question. You could envisage some sort of exotic construction, something a little bit more algebraic, that gave rise to some sort of infinite class of arithmetic progressions in the primes. And I don't think such a thing is known, and perhaps you would expect that, in fact, to be quite unlikely. Or you can envisage an approach where you try to count the number of arithmetic progressions in the primes. And of course, we'll have to make sense of that, because there are infinitely many primes, and we don't just want to end up with infinity as the answer. Although the first question was about infinity. We don't want to end up with infinity as the answer, because there are obviously these infinity of trivial arithmetic progressions. Okay, so we're going to look at this question of how many arithmetic progressions of primes are there. And to do that, I have a little bit of notation. So I'm going to write square brackets n for the interval 1 up to n. This notation is going to change halfway through the talk, not in an important way, but I'm going to symmetrize it, but I'll tell you when I do that. But to start with, this is the sort of standard notation. So we'll take square brackets n to be this set. And then I'm going to write Pn just for the set of primes less than or equal to n. So P sub n is the set of primes less than or equal to n. And then I want to introduce this counting function. Okay? So this is for any set A in 1 up to n. We'll write T of A to be this sum here. Okay? So it's the sum over triples, x1, x2, x3, where they're all those elements range between 1 and n, whole numbers between 1 and n, such that they solve this equation, which is to say such that they form a 3-term arithmetic progression, and such that all of the xi's are in the set A. Okay? So in particular, T of A includes all of those trivial progressions I talked about before, okay? Because if x1 equals x2 equals x3, then that certainly is the case that x1 plus x3 equals 2x2. And so this quantity here is at least mod A. Okay? And in fact, we're going to see that it's quite a bit larger than that in general. from which we'll find the presence of some non-trivial arithmetic progressions. It's perhaps worth saying, maybe it would have been worth saying on the previous slide, for this particular problem, the longer arithmetic progressions, of length 4, length 5, and so on, are sort of an error term. Okay? If I have a 4-term arithmetic progression, I obviously have a 3-term arithmetic progression. For sort of obvious reasons, I'm not interested in 2 or 1-term arithmetic progressions. And so, for the purpose of this talk, arithmetic progression almost invariably means 3-term arithmetic progression, and I'll highlight if it doesn't. Okay. So we define this quantity here, and the goal in some sense would be to estimate this quantity. Okay. So, this was estimated years and years ago by van der Korpen. So as indeed I expect many of you will know, in fact the answer is already, the answer to the first question is yes. And we'll come to that in a moment. But so van der Korpen provided an asymptotic for this quantity t of p sub n. So this thing here, this number, just to remind you from the previous slide, this is the number of 3-term arithmetic progressions in p sub n. Okay? And it has 3 components. Okay? And I want to talk a little bit about those 3 components. Just to make it clear. So the first one I want to talk about is this one on the end here, t of square brackets n. So that's just the number of arithmetic progressions in 1 up to n. Okay? And if you think about what this is, so t of n, it's the sum, and you can pick a starting point, x, less than or equal to n, and then you can pick some common difference, d, and you have to have it so that x is between 1 and n, x plus d is between 1 and n, and x plus 2d is between 1 and n. And if you do the sort of the algebra there, that gives you this range of summation of d. And this term here, if you think about it, is about n over 2 plus some error. And so this whole quantity here is about n squared over 2 plus bigger. And you can compute it more exactly in a combinatorial way, and I'm not so concerned about that. The point is, the main term here is this n squared over 2, okay? So, this term here is about n squared times some constant. This isn't particularly large, and this will turn out to be a constant dimension in a minute. Okay? So let me now turn to this term here, okay, which captures these sort of so-called local factors. I don't want to say very much about this. This is more to do with the number theory of the problem. All I'll say is that these factors arise from counting modular APs in Z mod PZ. Okay? And we're going to come back to counting modular APs later. I should perhaps say, so AP here is arithmetic progression. Okay? And the way they come up, if you think of this 2 as corresponds what this quantity ought to be for p equals 2, so you'll see for p equals 2, that would evaluate to 0. Each of these, there's one term in this whole product for each prime, and that term is just the ratio of the number of arithmetic progressions in the congruence, in the non-zero residues mod p, the set of non-zero residues mod p, divided by the expected number in a set of density, the same density as the set of residues modulo p. That's not quite right as I've said it, but that's the rough idea. So this, if you like, is a sort of scaling factor for each prime away from what you would expect in the random case. And I'll come back to that idea of the random case in a moment. Okay? For us, the relevant feature is this is some constant, and in particular, it's not 0. Okay? If it was 0, then this asymptotic would, well, I'd have to write it differently. I'd have to write some error term here, but it would be considerably less interesting. Okay? So there's some amount of number theory captured in this, and I don't want to talk about that. It's bigger than 0. It's the takeaway from this slide. Okay. The third and final factor then is this factor here, the sort of random factor. And I want to give just a little bit extra motivation for this, and this is the one to pay a little bit more attention to. Okay? And I want you to consider this a model like the model I just talked about. So suppose I take A in 1 up to n, and I pick it uniformly at random from sets of size alpha n. Okay, so think of alpha, in this case, going to be about 1 over log n, we'll come back to that. But alpha is some density, maybe like 1% or something. Okay? So doing that is basically equivalent to picking each element of 1 up to n independently at random with probability alpha. They're roughly the same. Okay? And so if you do that, you can ask, well, what's the expected number of arithmetic progressions in A? The expected value of T of A. Well, if you think about it, most arithmetic progressions in 1 up to n are not these arithmetic progressions with common difference 0, right? We estimated this quantity here to be about n squared over 2, and there are about n arithmetic progressions with common difference 0. Okay? So the vast majority of them have non-zero common difference, and that means that they contain 3 elements. Okay? So if you imagine that you're picking these elements from 1 up to n independently at random, then the chance that it contains all 3 of those elements is alpha cubed. Okay? So the expected thing, the expected number of arithmetic progressions in A, that alpha cubed times the total number of arithmetic progressions. Some error. Okay? And so then in our situation, we recall that, well, the size of the set Pn, that's just I of n, the number of primes less than or equal to n. So that's about n over log n, that's the prime number theorem. And so Pn over n, which corresponds to this alpha here, is this density of the primes. All cubed is about 1 over log n cubed. So if you like, this alpha cubed factor is this 1 over log n cubed factor. Okay? And that's why I'm calling this the sort of the random factor. Okay? So when we look at this expression as a whole now, we've got this term here, this sort of combined term, this is the number of arithmetic progressions in 1 up to n. And this combined term here is the number of arithmetic progressions you'd expect in a random set of density about 1 over log n in set 1 up to n. And then we have this factor here which tells us how the ways in which the primes deviate from random. Okay. So let's just return to our very first question, okay, just to see how this actually answers that. So suppose that there were a finite number of non-trivial arithmetic progressions. Okay? We wanted to show they're infinitely many, so suppose not. And this is a slightly peculiar way of deriving a contradiction here. So I'll try and go through this a little bit slowly. So then, the number of arithmetic progressions in Pn is just the number of trivial progressions, so that's just the size of Pn, plus some constant. Okay? And that's the finite number of arithmetic progressions, non-trivial arithmetic progressions in the primes. Okay? So let me say that again. The number of arithmetic progressions in Pn is just the number of trivial ones, plus, and then this constant. We're assuming there's a constant number of non-trivial arithmetic progressions in all of the primes. Okay? So that's asymptotically less than n over log n. On the other hand, so van der Kolk tells us that T of Pn is at least n squared over 2 log cubed n. And so here, I'm just using the fact that that local factor is at least a half. Okay? So in fact, he gives us a slightly better, he gives us an asymptotic, but for the purpose of this argument, we're not fussed at all. It's not going to make a big difference. Okay? And so that combining these two implies that n is bigger of 1. But we could pick n arbitrarily, which leads us to a contradiction. Okay? I appreciate that's a slightly odd way of setting it up, but that is how I set it up. Okay? And so, just to summarize, do the primes contain infinitely many arithmetic progressions? Well, yes. Okay? So fine, and that has been known for years and years. Okay. So there are 2 types of why I now want to talk about. Okay? The why that I mentioned in the introduction, which is the why of why we're asking the question at all, and I'm going to deal with that in a moment. But the first why I want to talk about is the why to do with proofs. Okay? So what we have there's an argument that van der Kolk has produced that shows us that the primes contain infinitely many non-trivial arithmetic progressions. Okay? The question is, why do the primes contain infinitely many non-trivial arithmetic progressions? Okay? A purpose for a proof is sometimes perhaps not so much to show that something is true, but to show why it is true. And so, in this particular case, it could be that the primes contain lots of arithmetic progressions just because there are lots of primes. Okay? So, I don't know what your sense of the word lots is, but I'm slightly defining my use of the word lots here. So I would think of maybe powers of 2, there aren't very many of them. They're quite sparse, but the primes there are shed loads, right? An awful lot of primes. And so that's what we're thinking of as sort of being lots here. Okay? So this is a sort of reasonable question, right? Van der Kolpert's argument somehow tells you that there are these non-trivial arithmetic progressions in the primes because of the particular structure of the primes. Okay? But it might be, as I say, it might be that simply there are lots of primes, and any time where you have lots of numbers, you get these arithmetic progressions. Okay? And we'll come back to why that's perhaps not always a completely trivial possibility. Okay? So let's perhaps start then by thinking what we might say. Well, so you might, if you were feeling very optimistic, or something, you might suppose that any subset of 1 up to n with size alpha n, so again you're thinking that for the primes alpha is about 1 over log n, you might expect that the number of arithmetic progressions is at least what we got for that random set. Okay, remember we did that random computation, it's at least alpha cubed t of n. Okay, so remember, this here is the number of arithmetic progressions in 1 up to n, so this is the expected number of arithmetic progressions in a random set. So sometimes it happens that random is extreme. So in fact, you already know that this is not the case, because if A is the set of primes, that constant in Van der Kolpert's theorem is in fact less than 1. And so this is not the case. Okay? So we could sort of revise our guess. So maybe maybe this is the case. I don't know, this is maybe alpha to the 1 billion, alpha to 1,000, something like that. So again, it'd be pretty large. Maybe it's the case that there really are, still quite a few arithmetic progressions. So curiously enough, that's also not the case. No polynomial of alpha will work, and that's a result of these guys Seoul and Spencer from 1942. And that's since been refined actually by this chap Berend in 1946 to give a slightly better argument. And since then, there have been some relatively small, which is not to devalue them, but relatively small improvements, but not any terribly substantial improvements. And in particular, they're all based around roughly the same idea. And in a nutshell, the idea is somehow, so if I have if I take the surface of a sphere in some, well, I'll just say start in 3 dimensions if you like, then if I take any 2 points on the surface of the sphere, then their midpoint is not on the surface of the sphere, right? So the sphere contains no 3-term arithmetic progressions, okay? It's really compact, okay? So what you can imagine is sort of fattening up the sphere a little bit and taking its intersection with a lattice, okay? And you could imagine that this sort of convexity of not containing these midpoints would be preserved by that process, roughly. And then you can imagine trying to embed that set into 1 up to n in such a way that you don't introduce arithmetic progressions, okay? Using a sort of, for example, something like a decimal embedding, but where decimal, the 10 tends to infinity in decimal. Okay? And it turns out you can do that. The details are nice. They're not super hard, but they're not trivial. And if you do that, and you let the dimension and the 10 in decimal tend to infinity at the right rate, then you get essentially our best known constructions. I don't want to say any more on that. But those constructions in particular give you a limit on how good this function can be. Okay? So I'm going to sort of skip over what that limit is, because I don't want to talk about that, and put a final guess in. Okay? So maybe we're going to make it sort of exponentially worse. So maybe so by comparison here, that's some polynomial, and then, so maybe t of a is at least this, we've got this exponential function, and then I've got the right number of minuses. So I think that is, yeah, I think that should be small. Anyway, make it so it's not obviously stupid. Right, this can't be bigger than 1. I think that's right. And obviously I've chosen 0.999 here to be some number slightly less than 1. Okay? So maybe this is true. And indeed, maybe it is. And this is sort of the first non-trivial case of this thing called the Roth-Turan conjecture. Okay. Why would it be interesting if this is true? Well, let me just do a little calculation for you. Okay, and relate this back to the primes. So, suppose then that I had a subset of 1 up to n, and it has this density alpha, the size alpha n, and it contains some bounded number of non-trivial arithmetic progressions. Well, then we would have this chain of inequalities, n plus big O of 1. So this n could be mod A, but it doesn't make any difference to just make it n. Okay? Would be at least T of A, which is asymptotic at least this guy here. And if you rearrange that, then you would get that this alpha must have density slightly smaller than some power of log, than 1 over log. Okay? So what's that saying? That's saying that if A is a subset of 1 up to n of density alpha, and it contains some bounded number of trivial arithmetic progressions, non-trivial arithmetic progressions, then in fact A must be very thin. Okay, they must be quite sparse, and that's what this is saying. And in particular, A must be sparser than the primes. Okay? So if this is true, then it follows just because there are lots of primes that there are these non-trivial three-term arithmetic progressions. And that, I think, is sort of the why you might be interested in this conjecture. Okay. So let me say what's known, and I'll go through this fairly quickly with just some highlights because it's not terribly edifying. But so for all of these, so these are results for any subset of 1 up to n of size alpha n. Okay? So Roth established the first argument, which is why it's called Roth's theorem, and Roth's thing, again, assuming that I've managed to make this less than 1, it's roughly doubly exponential. Okay? So it wasn't a great function, but it was the first explicit function here of alpha. Okay. Then Heath, Brown, and Semerady actually improved this exponentially. They said, well, this is at least e to the minus alpha minus c for some constant c. And I believe the reason for the sort of the 3-year gap here is Semerady spent a bit of time, possibly there's general publication slowness, but they also spent a bit of time optimizing c. So I believe that Heath, Brown got about 20, and Semerady got this around 4, maybe slightly better. Okay? But the smaller c is the better, right? Hopefully, again, I've got this. And then Bourgain has a couple of papers from 1999 where he gets it to be at most 2, and then 2007 where he gets it to be at most 1.5. And then in 2012 we were able to show that it's at most 1. And then there's a very nice recent preprint of Bloom from this year, which you find in the archive, which I would say is really a better proof that you can get to see this at most 1. It's worth looking this up. Okay? So all of these arguments are somehow within the same framework, but this Bloom in particular introduces a nice variant of something called Chang's theorem, which I won't have time to talk about, but it's worth reading. Okay. Right. So let me get on to the second why now. So the second why is why you might ask the question. Okay? So you might start by saying, okay, we're interested in solving linear equations in the primes. In general, there's the problem of solving linear equations, and it's reasonable to ask them to be solved in the primes. Okay? And in quite some generality, this has been addressed by Green and Chow in a range of papers, and I picked the one from 2010 to mention here, but there's a whole sort of corpus of work on this where they've rather comprehensively addressed when this is doable. Okay? The question, if you like, that we remain interested in is this question of why, the first why. Okay. So I want to look now at a bunch of different equations that highlight some different phenomena. And I'll go through this fairly rapidly because I've been a bit slow up to now, and I want to get on to a little bit about proofs, if I can. Okay? But what I'm going to do now is show you a bunch of different equations. So the first equation we looked at solving with these 3-term arithmetic progressions is this x plus y equals 2z, where we want x, y, and z to be primes. So here you might ask this question, right? So do the primes contain infinitely many solutions to this guy? It's not wildly dissimilar to the other one I wrote down, but of course it is in its properties, right? Because obviously the answer is no, just by some sort of congruence nonsense. So P2 has to be even, which means P2 would have to be 2, and then P1 and P3 are consecutive, and there aren't infinitely many consecutive. Well, it's just 2 consecutive primes. Okay, so no. So that's an equation where there's just nothing further to say. The our y question isn't interesting. But how about a slightly different one? P1 plus P2 plus P3 to P4. Well, again, the answer is yes, there are, and you can, van der Kolk's argument works just fine, and you can compute this, and they are, if you like, the expected number. It fits with the probabilistic model of the primes. And so then you could ask this question, is it because there are lots of primes? And the answer here is no, okay? And you can see this by considering this set A as the interval from n over 3 up to n, okay? So suppose I want to solve this equation, x plus y plus z equals w, in this set. Well, all of x, y, and z would have to be at least n over 3, okay? But then that means their sum is at least n, and maybe if n is not exactly divisible by 3, then their sum is in fact bigger than n, and so w can't be anything in the set. Okay. So this set A has no solutions to this equation, x1 plus x2 plus x3 plus x4, okay? Despite the fact that this set A is really quite large. Now, of course, you could complain a little bit that I'm just looking at some initial segment here, and I'm not giving you an infinite set, and so that seems a little unfair. Well, of course, I can just take sort of copies of this, and then take some copy for quite a bit later, and so forth, and I'll get a large set, and it will work just fine. The point here is that you can genuinely get a no answer to this question of whether you have solutions just because there are lots. Okay, so what about a slightly different equation? This one here, P1 plus P2 equals P3 plus P4. Okay, so again the answer is yes, and you can do van der Kolk's Jiggery-Pokery. And is it because there are lots of primes? Well, again, the answer is yes. But this time it's essentially a pretty straightforward application of Cauchy-Schwarz. And usually when people give talks around this area and they feel that they want to insert a proof, this would be when they would do that, and they would do the proof of this. And I've done that before, and it does work quite well. And I'm slightly regretting right now that I didn't choose to do that again. Anyway, that does work well. Okay, so the answer is, if you like, yes, and easy yes. Okay? So what about this equation? This is slightly more complicated. So P1 plus P2 plus P3 equals 3P4. Okay? So again, the answer is yes, fine. And you can do van der Kolk's stuff. And again, the question, is it because there are lots of primes? It turns out the answer is yes, and this is harder. This is a result of Bloom from 2012. But I would also like to, in fairness, direct you to work of Schoen and Shredov from 2011, where they don't consider precisely this equation, they consider slightly longer ones, but with much more, the sort of estimates they get are very strong. I don't want to say too much about that, except that, again, by comparison with the previous equation, the answer to this question is now yes, but it's much harder. Okay? So, to summarize where we've got to at this point, we're interested in solving linear equations in the primes. I'll sort of disappear off into my origins if I think of a reason why we want to do that. I think that's not an unreasonable thing to want to do. I'm just going to assert that. We introduced at the very start this idea of counting rather than finding some other construction. This idea of counting arithmetic progressions, or in general solutions to linear equations in the primes, is good because this lets us introduce a lot of analytic techniques. Okay? We've seen that different equations behave differently. That was the last wad of slides. And in particular, the arithmetic progressions are less well understood. I showed you a bunch of equations on the previous slides where we could ask this question of whether they had infinitely many solutions in the primes or not. And we could also ask this question of whether it was for reasons of there being lots of numbers in the primes or for other reasons. Okay? And in each of those equations, we could answer both of those questions, yes or no. So with arithmetic progressions, we can't answer the second question. So I want to claim that if we're interested in this question of solving linear equations, then one of the harder ones where we don't understand what's going on fully yet are these arithmetic progressions. And that's why there are other equations, but they're sort of a prototypical example, and that's sort of why we're interested in this. Okay? And so we want this proof to explain why we need this. And so and then to summarize where we've got to, I want to just record Roth's theorem with good bounds. Mainly because, again, I have accidentally given a talk like this without stating Roth's theorem before. And so this is Roth's theorem as we know it today. Okay? I suppose this is low, actually. We can do slightly better. So if A is any subset of 1 up to n of size alpha n, then the number of arithmetic progressions is at least, basically, exponential n 1 over alpha times the number of total arithmetic progressions there could be. Okay? And any improvement in that 1 would resolve this question here. Okay? Right. So let me talk a little bit now. I think I've got about 15 minutes, and I want to talk a little bit about proofs. Okay? Now, what I want to say about proofs is I want to convince you of this role of approximate proofs. Okay? And I'm going to do a little argument using approximate proofs, and that argument is going to be closer to the actual proof of Roth's theorem than it appears to be. Okay? It contains a number of the key ideas, but is a little bit simpler. Okay? So I want to start by saying, well, you could question, I don't know, I don't mean this in a categorical sense, I just mean in, I don't know how queasy or not you feel sense. Counting arithmetic progressions in 1 up to n, there was this sort of slight combinatorial ingredient, right, of, we don't have this wraparound property, right, so you have to sort of, you've got your 3 points in arithmetic progression, and you've got to sort of say, well, that they, the arithmetic progression doesn't loop round 1 up to n somehow, and that introduces this factor of a half here. So I mean, I suppose it's a natural enough thing to count, but it's slightly simpler to count modular arithmetic progressions. So I haven't defined this guy here, but it is the obvious thing, right? If I want to count modular arithmetic progressions, that is, arithmetic progressions in 1 up to n mod n, okay? Then I don't even need to engage brain, right? I just pick a starting point and I pick a common difference. And that is precisely the number of them. And so with this way of counting, there are exactly n squared. Okay? And so I claim this is a sort of slightly simpler setup from this one. Okay? And so that's basically because Z mod nz is closed and 1 up to n is not. Okay? And what I'd like to do, and what happens in the sort of theory of approximate groups, is you try to take your operation here on 1 up to n and make it roughly closed. Okay? So in general, of course, it's not closed, because if I take a couple of numbers, each of them bigger than n over 2, and I add them together, I get something bigger than n. Okay? So I've got the group operation on Z mod nz, just takes the pair x, y, and sends it to x plus y. So now, I want to think of an approximate group operation, and it's going to involve essentially introducing an asymmetry here. Okay? We recover closure by introducing an asymmetry. And the idea is, if you take the interval 1 up to n, and you take a much smaller interval, and you add it to the large one, most of the time you stay in the large one. Okay? So I take a long interval, and I perturb it a little bit by a small interval, I mostly stay in the large interval. Okay? So I'm mostly closed in some sense. Okay. So I'm going to pick this parameter n prime much smaller than n. Okay? And how much smaller will tell you the quality of the approximation you're interested in. And so then I take my usual operation, but this time from 1 up to n cross 1 up to n prime. And I think of it mapping in, of course, it isn't a map or anything, right? Because it doesn't always end up in 1 up to n. But sort of, morally, you think of this as going to that. Okay. And indeed, there are exactly n times n prime pairs here. And the vast majority of them map into 1 up to n, right? If n prime is much smaller than n, then the total number of pairs here that map into there, under this map, it's almost 100% of the pairs, okay? And that's the notion, if you like, of sort of approximate closure that we have. Let me say briefly that, of course, Z mod nz also has an identity and also has additive inverses. And 1 up to n has neither of those things. Those are kind of easy to add in, essentially by shifting. And this is where I'm going to just slightly shift my notation. I'm going to symmetrize. I'm going to send n to minus n over 2 up to n over 2, and then prime to minus n prime to 2 up to n prime over 2. Okay? So, I mean, I know it's obviously bad to change notation halfway through a talk. This is somehow not, this is not a particularly important change. Okay? I just, well, it's important, but it's not an expensive change. Okay? As I say, it's just to add in additive inverses and an identity. Okay? The reason that we can afford to do this in this situation, you can imagine it just as a translation, basically, of where 1 up to n was. And if I took my original set A in 1 up to n, then because arithmetic progressions themselves are translation invariant, if I translate A backwards by some amount, it will live in minus n over 2 up to n over 2. And counting arithmetic progressions in that setting will not be will be exactly the same as counting them in the translated setting. Okay? So the translation invariance comes to our rescue. Right. So I then need to introduce a sort of an asymmetric operator here, right? So I had T of A before, and now I'm going to have T of A, comma A prime. And there are sort of two ways of defining this, depending on whether you characterize your, you're looking for solutions to this equation, or whether you're looking to parameterize the solution to this equation. I don't want to say a whole lot more than that. But in this instance, the correct way to introduce this group operation, this approximate group operation, is to make these x2 values lie in this smaller. So I imagine now I've got a situation where I've got A in 1 up to n, and A prime in 1 up to n prime. And I'll tell you how you come up with A prime in a moment. And then I will count arithmetic progressions where, if you like, the two endpoints are in this set A, and the midpoint is in this set A prime. Okay? So then I can just, for completeness, I can then compute the number of arithmetic progressions in between 1 up to n and 1 up to n prime. And if you insert the approximate group fact, or approximate closure property I talked about before, it's easy enough to compute that this is roughly n times n prime plus some error term. Okay? And this is good. Crucially, there's not a sort of n over 2 here. Now, what we'd like to do, we've got our original set A, now in minus n over 2 up to n over 2, and we'd like to say, well, fine, set A prime to be A intersect 1 up to n prime. Okay? Now, of course, you can't do that because, well, A could be the set minus n over 2 up to n over 2, but with the middle segment removed. Okay? So then A prime would be empty, right? And this would be a pretty ridiculous count, it would just be 0. Okay? But somehow A, of course, if A really is designed like that, A has loads of arithmetic progressions. They're just not right in the middle. Okay? So this isn't precisely what we want to do. So the thing I want to prove now, pretty swiftly, is that we can set things up so that we can find intervals. We can set up A so that A on some smaller interval and A prime on some even smaller interval are both fairly large. Okay? And the argument for doing that will be an iterative argument very similar to Roth's, the approach to Roth's theorem. So if people who know a little bit more about this, in Roth, you can think of Roth's theorem as finding some kind of structured set on which you control the U2 norm. And what we're going to do here is basically find a structured set on which you control the U1 norm. Okay? And the kind of the overall argument for doing that is not utterly dissimilar. Okay? So this is the lemma I want to prove. Okay? So we imagine we've got this set A of density alpha n, and epsilon is this parameter, effectively some sort of approximation parameter. Okay? So then there is some n prime, okay? And the point about n prime is it's not too small, and I'll come back to how small in a moment, and some x, such that A on this translated interval, n prime, has large density, right? Alpha minus some error term times the length of the total interval. And then A also on this smaller interval, which is about epsilon times the length of the larger interval, also has this larger density. Okay? So effectively we're replacing before n by n prime and n prime by n double prime. Okay? So the approach to proving this is going to be iterative, and I've just been told 5 minutes, I'm going to be quite swift. Sorry, yes. And so now to use this, we could just put A prime is A on that interval, and A double prime is A on that interval, and then we would have this inequality, and you could estimate this guy. Okay? So to prove this, you can use convolution. Okay? And convolution, for my purposes, will be defined like this. Okay? And the reason it's useful is because 1A convolved with 1B, evaluated at x, is just the size of A intersect x minus b. Okay? So we're going to look at B being one of these sets, minus n over 2 up to n over 2, or minus n prime over 2 up to n prime over 2. And so it's symmetric. So B will be symmetric, so this minus could easily be a plus. And the way you proceed with all these arguments, it's an iteration. So you suppose, so on the one hand you have a situation where A might have increased density on some interval, in which case you pass to that interval, and you hope that that interval is long, and you start the argument again. Or if A never has increased density on some subinterval, then you use that to estimate the quantity you want. Okay? So what we're going to do is say, suppose that A never has increased density on a subinterval. Okay? So this quantity here is just A, the size of A on the set x plus square brackets n prime. Okay? That has size at most n prime, and we're saying it's got not much bigger density than alpha, than the original set A has. Okay? So if you suppose that, you also know that the average density must be the density of the set A, and that's using approximate closure. Okay? And so then that means the absolute values, if you like, the L1 norm of this deviation is also small. Okay? It's because the maximum value is never large, and the average value of this thing inside the mod science is 0. And similarly, you have this for the smaller interval. And so when you add those two, and I know I'm going very quickly now, but what I want to summarize these couple of slides by saying is just that they're, by some relatively basic algebra, you can come to the conclusion that if we had the hypothesis that the density is never larger than some epsilon larger than the original density, then you can get some x where both of these quantities are small, which means that both of these are in particular large. In fact, they're close to alpha, but you don't care if they're much. The idea of them being bigger doesn't worry you. Okay? So then you have this iteration scheme. So either A has density at least alpha plus epsilon on some x plus n triple prime, where n triple prime is not much smaller than n, or you're done. Okay? Now you can, with this, if density goes up by epsilon at some stage, that can happen at most epsilon inverse times. Okay? So that means you can be in this first case at most epsilon inverse times. So within epsilon inverse scenarios, you must be done. Okay? So that means that the desired conclusion holds for some n prime, at least of this size, right? You've got this epsilon squared applied epsilon inverse times. So that is the form epsilon to the big O of epsilon inverse. Okay. So that's given us a method now for replacing A by a pair of sets in effectively a pair of intervals. Now, I think time-wise, what I want to do is just say then how this relates to the rest of Roth's theorem. So Roth's theorem overall then fits exactly within this framework, but rather than trying to fix the density of A on some intervals, you try to control, in fact, which is the same as saying that 1 sub A convolved with an interval is roughly constant. You want to also show that 1 sub A convolved with 1 sub A is roughly constant. And that's a harder thing, and you do that by uniformizing the U2 norm. I'm not going to go into the details of that. There's a tool you can use for doing that, which is the Crout-Cesas lemma. And there's a refinement of this due to Crout-Cesas and Laber, which is a little bit stronger and give you, in fact, the better bounds. When you apply those results, you also need to generalize your notion of approximate group, not from just these intervals 1 up to n, but in fact, if you think about it, to more generally any convex body or any set of any lattice intersected a convex body, which also has this property of behaving like an approximate group. Think about it, if I take a ball and add a smaller ball to it, I mainly stay within the big ball. Okay? So those two ingredients combined, and I mean that's where all the details are, within this iterative framework to establish what we know about this. But I will stop there.
Thank you very much. Are there any questions? If not, we give you a small present from the organizers. Thank you very much.